Hey, welcome back to No Bias, where we discuss the emerging and ever-shifting terrain of artificial intelligence and machine learning. In our first episode, we walked through the differences between AI and ML. If you missed that one, head back to episode 1. Today, we are going to dive deeper into two machine learning approaches, supervised and unsupervised learning. We will offer definitions and then talk about some exciting business use cases. I'm your host, Melody Travers, and joining me are machine learning researchers Nikhil Kumar and Saurabh Bhagalkar. Hey, Saurabh.
Hey Melody, how's it going?
Good. Hi, Nikhil. How are you?
I'm doing well. How are you?
I'm good. Thanks for coming in. Arthur Samuel, a pioneer of machine learning, described it as giving computers the ability to learn without being explicitly programmed.
You always have codes.
Well, as Wittgenstein said, when we can't think for ourselves, we can always quote. So let's start with, what is supervised learning?
Sure. So supervised learning is one method in machine learning which uses label training data. What supervised learning does is it supervises the machine learning model for a specific use case. So let's take an example of an image classification, which is one supervised machine learning method. So let's take a simple example, a binary classification example of cats versus dogs. If I want to recognize this picture is of a cat or a dog, I need an a priori information that the image that I have currently, which is a single data point, is labeled as a cat, and the second data point is labeled as a dog. So this is what I mean by labeled training example. So the supervised training approach is we supervise the model to make sure you make the correct decisions or the right predictions, and over time it will learn. So it's not actually finding any patterns or anything like random patterns within the data, but we are explicitly teaching the algorithm that this is a data point which corresponds to a specific example, and this is a different example, and you need to identify that.
Sure. So if you're with a small child and you walk down the street and you point to a
Exactly.
dog and you say, "What's that?"
Yeah.
And they go, "Wait, I've learned this one before. You've told
Yeah.
me this. Is that a cat?" And you go, "No."
Yeah.
And you're like, is it a squirrel? And you're like, "No."
Yeah.
Dog? Yes.
Yeah, exactly.
So we're doing that for the algorithm.
And then you give the child a chocolate or something. So that's a reward for the algorithm or the model.
And then they're really excited
Yes,
about dogs.
Exactly. So
Cool.
yeah, that's an overfitting problem there. So but yeah, in a general case, it's basically if you make the right predictions, you reward it. If you make the wrong predictions, you basically do not reward it. So in that case, it learns it using a supervision, and a supervision can be modeled as a mathematical function. So that's why this is called supervised machine learning approach.
What about unsupervised learning?
Unsupervised learning is on the other side of the learning spectrum, and it's all about more of a data-driven approach to analysis as opposed to a task-driven analysis. So in everything you just said, is an image a dog or a cat? There's a specific question that the model learned, and the model outputs a yes or no to a question like that. On this side of the spectrum, we are looking at the data as a whole and then seeing, are there specific structures or patterns, groups, clusters, anything like that in the data, without any real notion of a right or wrong or an explicit thing to do. It's more of, here's a data set and here are a bunch of clusters that naturally exist in your data. And it does that, and that is sort of, that process of learning is the unsupervised part of it.
So there's no teacher, or parent or advisor telling you yes or no. You're just kind of in an art class scribbling and they're like, "Oh, that's beautiful."
Exactly. That's right.
Cool. Great. So can you guys give me some use case examples of, let's start again with supervised learning.
Sure. Use cases for supervised learning can be in a lot of fields, from computer vision to natural language processing. Let's take an example of a self-driving car. A self-driving car, if you go right now in Phoenix, Arizona, or Bay Area, you can see Waymo, which is owned by Google, going around towns and having this little metal thing which is rotating extremely fast. And people are always wondering, like, how do self-driving cars work? But this is actually inherently a supervised learning problem. A car is learning to drive by itself by looking at its surroundings and recognizing objects in the surroundings. The objects can be the road, the sky, a pedestrian walking across the road, the traffic lights, and accordingly, by seeing these objects, it is taking some actions. And these actions can be using a brake when a pedestrian or a child walks on the road suddenly, or slowing itself when the speed limit is below the limit that at which the car is moving forward, and other examples like this. So this is an inherently supervised learning problem.
So, what would you use unsupervised learning for?
In a lot of the data science projects I've worked on in the past, clustering is probably the most common technique to do that. So that is literally forming clusters in your data. And then from a use case perspective, a very common one is anything along the lines of market segmentation. So for example, you or any business may have a large amount of demographic data, socioeconomic data about your customers, and you want to see, are there naturally existing groups in that? So do you have, for example, a high income subset? Do you have a low income subset? Do you have an urban subset, a suburban subset, like that? So in that example, you would look at your data, you would see how close certain subsets of people are to one another, and then if it's sufficiently close enough, you would assign that to a cluster, and then you would do some kind of post clustering analysis to sort of build a persona for each cluster. So for example, you to see if that is in fact a high income cluster versus a low income cluster.
So, it seems a lot more exploratory in nature. And with the supervised learning, it sounds like we have the insight to begin with and then provide that to the algorithm. Whereas in unsupervised, they are giving us some information and then we have to sort of make sense of those clusters. Is that right?
So to reiterate a little bit what Nikhil said, in unsupervised learning, we do not have specific label training data, but we are finding or making sense of an existing data set in there. So we don't know what we are specifically looking for, but in the end, we are basically finding patterns in it, and these patterns might be useful in the end, might not be useful.
That's right, and it's very data driven. There's less direct supervision in that you're not supervising the algorithm, but to sort of extend that further, there's less supervision in terms of the business question or the research question being asked, in that there really isn't one. It's more of, let's just see what this data looks like. Let's see what sort of hidden structures are there.
I also heard that unsupervised learning is used for compression, so you can figure out what is used over and over again, and maybe you don't need that 12,000 times. You only need that once to represent the whole.
That's right. Yeah, that's another good use case of unsupervised learning, and that kind of falls under the family of dimension reduction. So, and what you just highlighted is a very common application of that. So oftentimes in business, industry, and science, you may have a data set, a very, very big data set, and by big, in this case, we mean wide. So a lot of features, and maybe we have the hypothesis that we have a lot of features, but there's probably some redundancies among those features, or there's some repetitiveness amongst those features, and we want to see in some algorithmic way if only a smaller number of features can still explain the whole picture, which will, and if that is the case, we can then take action on that by reducing it to just those smaller number of features, which will make the data smaller and easier to process and analyze and move downstream in your analysis.
I've read that teams have had a lot more success with finding concrete business applications for supervised learning than with unsupervised learning. Why do you guys think that is?
Yeah, it kind of makes sense, doesn't it? Because we in supervised learning, we know what we are looking for. We are very specific to a certain use case, say for voice recognition or entity recognition or facial recognition, um, segmentation of images. So you have a plethora of applications in this specific use cases, and there is huge market for this. Whereas for unsupervised, you do have a lot of applications, but those are more general in nature, which do not have their own specific applications. So, and the availability of high quality labeled data actually is very useful to like achieve that specific use case scenario. And we can have endless applications with supervised learning, and that's why it's more successful in fields which have a lot of information like computer vision or natural language processing, because there is a lot of labeled data from specific region or specific people that can generate all this data.
That's right. And I think to add to that, one of the reasons why unsupervised learning is at times seen as maybe a little more incomplete is that when you're done with unsupervised learning, so for example, if you have your clusters, there's sort of the natural question of what do you do next? And that's kind of where unsupervised learning tends to break down. So it's actually common that you might do a market segmentation exercise and you form your marketing personas, but then your stakeholder will might come to you and say, all right, this is great. This is a great summarization of our market. What do I do next? How do I actually monetize this, or how do I move forward? And then that's really where unsupervised learning ends. And that process really is when supervised learning turns on. And then you have to build a predictive model to act on those segments.
Yeah, and also unsupervised learning can also be like a precursor for supervised learning. We can use that for some kind of pre-processing applications to reduce the complexity of our models. And using those clusters can be used as for easier feature extraction for the supervised learning mechanisms.
Or even just data exploration for that matter. It's really just, I like to view it as sort of a chain of analysis. And you might start with data exploration, which might include a great deal of unsupervised learning, and then the more prescriptive analysis, which is the supervised learning aspect of it.
So Saurabh and I went to CVPR together.
That's right.
And there we had a self-proclaimed spy from Google Brain who is working on the problem of unsupervised learning. And I go, oh, what do you do? And he goes, oh, we're trying to put you guys out of business in a very like kind of joking way, but kind of not joking, right? We're a data labeling company. And there's been so much excitement about unsupervised learning because of this idea that you just set an algorithm loose on the data and we just sit back and do nothing, right? And so I was talking to him and I go, okay, so how close are you guys? And he was like, well, we're pretty far off, right?
Yeah.
So I was like, okay, good. But yeah, let's talk about that a little bit more. Why would we want to move away from supervised learning, and why does that seem like maybe a pipe dream?
Yeah, I think what you're mentioning sort of speaks to some of the strengths of unsupervised learning. And it's certainly not the case as a data scientist, as a machine learning person. I'm not at all anti-unsupervised learning. I think there's a great deal of insights that can come from it. The main thing is that one of the things, and speaking of strengths, you can kind of think of it as a relatively inexpensive form of analysis. So when you want to do supervised learning, that's great. You want to build a cool machine learning model. It's inherently a more expensive task, primarily because you need labeled data. And that is often, there's all sorts of expenses associated with acquiring labeled data. Unsupervised learning, to your point, you kind of can set it free and it'll learn something. It'll learn what, various hidden structures in your data, and then it'll come back to you with some analysis. On top of the fact that there's no right or wrong. So it's almost like in some ways, there's always going to be some insights to it. And I think that speaks to its strengths, and that speaks to its strengths really as a data exploration technique more than anything.
Mm-hmm.
I would like to add to Nikhil's point is in supervised learning, one more weakness is you need a lot more expertise and lot more research and development efforts, because if you take, for example, computer vision or natural language processing, which use deep learning, which is a specialized form of supervised learning, there is a lot more expertise, lot more computational power, and many hours of research, as like even unsupervised needs that, but at a lower scale, because the algorithms are not that complicated as opposed to supervised learning.
Yeah, you need that domain expertise.
Domain
right?
expertise, and on top of that, you also have the need for high quality training data.
Sure.
Even just having the computational architecture to support a
Yes.
deep learning solution is by no means trivial.
Right.
And again, adding to the expenses associated with supervised learning.
Yeah, I was reading about that, how you need domain expertise not only to build the features of the model, but also to build the sort of tasks and workflows and everything around the actual labeling process.
Like the ML ops or the machine learning ops,
Yeah.
like DevOps, and it is a big area in itself, because building a model and architecting the model is one thing, but building the surrounding architecture that can use this machine learning model is a completely different story altogether.
Sure.
It's also very complicated.
Transitioning it from something that is theoretical and research oriented towards a business application.
Yeah.
Yeah, that totally makes sense. Okay, well, we are getting to the end of the episode. What are the coolest applications that you guys have heard of?
So there is this new paper by Google, which is actually the input for your machine learning model is a voice, right? And the output is a face. So if you have a specific frequency of voice, the model has been trained on millions and probably billions of voices or variations of that voices, and then it will generate a face for that specific voice. It might not be a real person, but it can be a real person if the voice is already in the database. So that's a fascinating example for me.
Yeah, that's so weird. I can't tell you how many times, especially with podcasts, where I'll have this idea of what the person looks like and then see a picture of them and I'm like, what? Who is that?
Yeah.
So I don't know how they would match that up, because, you know, I've seen billions of faces too and heard a lot of voices, and I'm
Right.
pretty much always wrong.
Yeah, it's really cool. I think that the paper you were referencing, they have a lot of celebrities, right? And you
Right.
hear their voice, and then you hear what the model inferred as the face, and it's a cool paper to check out.
Yeah, absolutely. Maybe we'll put a link on our landing page to that. How about you, Nikhil?
I think on the other learning spectrum side of the learning spectrum for unsupervised learning, there's a lot of cool efforts to basically make the clusters as precise as possible. So, you know, in the traditional way of doing that is by using a distance metric. So if you think of your data as points that are literally close to one another, in other words, have a short distance apart from each other, you would cluster them into one group. Points that are far apart, have a far distance apart, are clustered into different groups. And there's a lot of cool kind of math and just research into making that as robust as possible, including density instead of distance. So it really does a cool job of doing of making clusters as precise as possible, even if maybe when you're looking at them, they may even look far apart, but their distance is misleading. Or, you know, when you have edge cases like that, this density-based clustering can prove to still make precise clusters.
Can you give an example so that I can follow a little bit better?
So there are some cool examples. So if you sort of think of this on a graph, you may have some data points that form maybe a spiral. So you have points that naturally exist in a spiral, indicating that there is some naturally existing cluster or group. However, if you use your traditional distance metrics, it may not do the best job of viewing them in the same cluster, because there are still parts of a spiral that will look far apart. But if you factor in the density of it, or kind of a more multi-dimensional way of looking at it, then it'll still look close together, and then you can still be able to infer that they're in the same cluster. So when you have examples like that, that could be a cool reason for why you might want to use density-based clustering.
Yeah, I'm like picturing galaxies right now.
Exactly, and I'm sure that would be a really cool area of scientific research. Yeah.
I'm an animal lover, and so the one that I read about that I thought was really cool was that DeepMind developed a machine learning model that can label most animals at Tanzania's Serengeti National Park. And I was like, okay, labeling animals like, cat versus dog, that's pretty basic. But they have a huge array of species there. And they said that it takes volunteers 9 months to do the same kind of labeling that the algorithm knows how to do now.
That's pretty cool.
Within minutes. So that has made tracking animals a lot easier within the park.
Oh, that's good.
Yeah, and it speaks to also how I imagine for a project like that, you got to have a really robust database of labeled animals. So like this animal is this precise species, and I'm sure it's a really interesting, just even looking at the database would be really fascinating.
Yes, absolutely.
Yeah.
I would like the infographic version of the database.
Right.
I'm sure you would like to get to the raw data.
Right.
Cool. Well, thank you guys so much for joining me and this discussion about supervised versus unsupervised learning. If you can't already tell from our title, we are super passionate about the subject of bias. Bias can have devastating results, especially when you feed biased data into your algorithms. So, next time we're going to look at some examples as well as methods for mitigating bias. See you then! This episode was produced by Melody Travers. Thanks again to our experts Nikhil Kumar and Saurabh Bhagakar. Music by Melody Chabrellin and sponsored by Allegion, integrating human and machine intelligence to produce ground truth data for enterprise AI and ML projects at any scale. For more information, check out our website, allegion.com. Please tell your friends and don't forget to subscribe. See you next time. Thanks.